Okay, this team challenge that we did this week was a thermodynamics problem, and I actually stole it right from the first page of the test from last term. So it ties in some of the concepts that we learned in the first unit on pH and pKa with the thermodynamics that we're learning now. So the question asks, you know the pH of a 0.1 molar solution at two different temperatures, and you're asked to find the delta G naught for the dissociation of this acid, which is the loss of a proton at the two temperatures. So what am I asking here? I'm asking about this HA going to H plus and A minus. This is the reaction. That's what the words say, the dissociation of a weak acid. I'm telling you that the pH is equal to 2.46 at 20 degrees. And I'm telling you that the pH is equal to 1.80 at 40 degrees. So, from these pHs, we can calculate hydrogen ion concentrations because we know that the pH is equal to the negative log of the hydrogen ion concentration. So we can calculate the hydrogen ion concentration to be, in this case at 20 degrees, the hydrogen ion concentration can work out to be 0.00351 molar. And at the other temperature, we can work out the hydrogen ion concentration just from the pH to be 0.0157 molar. Okay, now what is this going to tell us? Well, basically, we're looking for a delta G naught here. And so what does that have to do with the pH? Well, we know we have an equation that relates delta G naught to the KEQ. And for an equation such as this, KEQ is a K equals Ka. It's what the Ka is, a specific kind of KEQ. So we know that Ka is equal to the concentration of H plus times the concentration of A minus all over the concentration of HA. So since we know H plus, we also know A minus by assumption, and we can calculate the actual HA concentration since we know the initial and we know the final concentration of H plus. So we can substitute in here, this is equal to sort of x squared over 0.1 minus x, if you like. I didn't even factor in the x when I did my calculations, but it's more correct to do so. So if you put these numbers in here, for the first example, we have 0.00351 squared over 0.1 minus 0.00351. Like I said, I didn't bother to factor this in. It's small. That gives me a Ka equal to 2.46 times 10 to the minus 3 at this temperature. Sorry, that was at, which one is which here? I've done it only at 40 degrees. I seem to have done it at 40 degrees. Hold on. Just back up there. I've written it out for myself at, at 20 degrees it comes out to 1.23. Sorry, looking at the wrong place. Times 10 to the minus 4 at 20 degrees. So once we have a Ka, we can calculate delta G naught from that Ka. Delta G naught equals negative RT ln KEQ, or Ka in this case. So we can simply just plug that value in. The negative times 8.3145 joules per Kelvin mole. In this case, our temperature is 20 degrees, which is 293 Kelvin, times the ln of our Ka. So in this case, that gives us a value of 2.19 times 10 to the 4 joules per mole. I do exactly the same calculation for the other temperature, and I would get a delta G naught. So here's the delta G naught at 20 degrees, see, and the delta G naught at 40. I'm going to let you do the numbers yourself. I've got all the meaningful numbers here, of 1.56 times 10 to the 4 joules per mole. So what this part one of the question has done is allowed us to figure out two delta G naughts, okay, at two different temperatures. All right, so that's the start of the question. The next part is to determine what delta H naught and delta S naught are. If they're independent of temperature, what are the values of these? So I'm going to erase everything except the answers here. And we're going to figure out what delta H naught and delta S naught are. So this is a case of two equations and two unknowns. We have to use the equation delta G, or delta G naught, equals delta H, or delta H naught, minus T delta S naught. Okay? So we have two delta G naughts, and we are going to solve two equations and two unknowns. So I'm going to say 2.19 times 10 to the 4 joules per mole equals delta H naught minus that temperature, 293 Kelvin, times delta S naught. And we have another equation, which is that this delta G naught, 1.56 times 10 to the 4 joules per mole, is equal to delta H naught minus the new temperature, which would be 313 Kelvin times delta S naught. Two equations, two unknowns. Do the math however you like. What I would do would be to set delta H naught equal to 2.19 times 10 to the 4 joules per mole plus 293 Kelvin times delta S naught is also equal to this, which is 1.56 times 10 to the 4th joules per mole plus 313 Kelvin times delta S naught. So what you do here is just put all the numbers on one side, all of the delta S on the other, divide out the temperature, and what you are going to get is a delta S naught of 315 joules per Kelvin mole, and a delta H naught of 114 kilojoules per mole, or 114,000 joules per mole. Okay, so that's two equations and two unknowns. We move from that to the next question. It says, at what temperature is this reaction at equilibrium? And this is simply a rearrangement of the fundamental delta G equals delta H minus T delta S equation. When we're at equilibrium, delta G equals 0 at equilibrium, right? So we can say 0 equals delta H minus T delta S. Put this stuff over on the other side. T delta S equals delta H. And we can solve for the temperature at equilibrium as delta H divided by delta S. Put them both in the same units there. We say 114,000 joules per mole divided by 315 joules per Kelvin mole. And look at that, we're going to get the right units of Kelvin. This gives 363 Kelvin, or 89 degrees Celsius. So this is the temperature at which this system would be in equilibrium. And the final question on this team challenge was to then say, all right, what is delta G naught prime? So this is where pH is equal to 7, or H plus concentration 10 to the minus 7. So we have an equation for this that we'll use, and that is that delta G naught prime is equal to delta G naught plus RT ln H plus. Okay? So we do have to figure out what delta G naught is. This question was at 25 degrees. So we have to figure out what delta G naught is at 25 degrees. We solved it at 20 and at 40 earlier. But at 25 degrees we're going to have to figure it out. So we're going to have to solve delta G naught first is equal to delta H naught minus the temperature of 25 degrees, 298 Kelvin, times delta S, delta S naught. Okay? So if you calculate that out, you get, I've got it somewhere written here. I've only done the math all the way through. So you have, when you figure this out, delta G naught, you substitute in here, and delta G naught prime would then be equal to the delta G naught we just figured out, plus R times the temperature, 298 Kelvin, times the ln of 10 to the minus 7. Okay? And that gives us a value when you figure it all out of negative 19.6 kilojoules per mole. Okay, so the tricky, I guess the slightly tricky part for this question is to remember that you've got to use the delta G naught at the temperature in question. So the temperature in question is 25C, you have to use 298 Kelvin. So you have to do this step of figuring out what delta G naught is. Okay, and then you factor in RT ln H+. So that's how you do that question.